Okay, so in the next example we will create so we already have this catenary chain. A catenary chain means a chain that is hanging. So there was a question: can we disable the preview of nodes and instead have just the lines? And yes, the answer is that you can. You just have to use the O output, not the V, and you have to turn off the preview, right? Because V are all the nodes or all the vertices in the system. You don't want to see them, or you don't need to see them. And the line goals, they are output here, and you can use them. Except of course there are a lot of null objects, but you have the lines as well. Why do we have the nulls? Because this O output is structured the same as the goal objects list that you put in here. So your list looks like you have two anchors, then you have, okay, that's interesting. Actually, it's a bit, okay, it's not the same. That's strange. Okay, anyway, you have the lines output here, so you can just input the line, them into line components. You will get the nulls, of course, but it doesn't matter. Anyway, in the next example, we will create a tent which will be formed by a surface anchored in the four corners, so something like that. And in this case, we will replicate Heinz Isler's experiments. I don't know if you remember them. I think that I showed them on one of my presentations. So Heinz Isler was doing this kind of experiments where he just hung a piece of material, a piece of fabric by its corners, and then they formed something like that. And he did that to just create forms that are perfectly balanced. So that was something like that, a dome. So he was creating this kind of elements. And we will replicate these experiments with Kangaroo, but we will invert the force, so the particles will not be dragged by gravity, but a reverse gravity, so this will be, like inflated. So we are making the models more complex. As you remember, we started from a single particle, then we had a hinge, so a line connected to an anchor, then we have the catenary structure, the chain, and now we will move forward and create a tent. So in this case, we need to start from a surface. So let's please create just a surface in Rhino. It doesn't have to be a square, whatever, just flat surface. And create a reference in Grasshopper. Okay, and now probably the most, or let's start from converting it to a proper model. So I told you about discretizing. We need to convert the NURBS geometry into a mesh. And the best way to do that is, in this case at least, is to use mesh surface component. And I will explain why mesh surface. And why not, for instance, mesh brep, but in this case it should work similar, I suppose. Not really. Okay, so the difference between mesh brep and mesh surface is that in mesh surface you can explicitly tell Grasshopper how many divisions in both directions it should make. So it's similar to isotrim and divides the domain that you might remember from one of the first tutorials. So mesh surface will always give you a nice grid of rectangular faces. And this is very important because in Kangaroo we prefer regular rectangular grids. We wouldn't like to have a surface which would be tessellated maybe like that. We don't want triangles because we want the lines that the edges of the mesh will represent later the forces or the lines that will keep the model together. So they should be as similar to each other as possible. So the length of each of the lines should be similar, and also the topology matters. So of course this would be a valid mesh, nothing wrong with it. But the topology of such a mesh let's say that's just not it's incompatible with Kangaroo. So once again, we want to use mesh surface. We want to create regular rectangular grids. So let's now just tweak the settings of mesh surface by changing U and V count. Depending on what are the proportions of your surface, you need to adjust U and V slightly so that the cells are as similar to each other or as similar to a square as possible. Of course you could calculate that, but let's not waste the time on that. So yeah, let's say that these look like squares, more or less. So that's what we want to have. And now, basically, what we need to do is we need to extract all the edges. So we would need to extract all the edges of this mesh and treat them as lines in our catenary structure. So that's what we would do if there was no component to automate that. So every vertex of the mesh will become a node with a unary force applied to it, so a gravity. We will have some anchors, probably the corners will be our anchors, and we will have those lines that will keep everything together. So first let's find the anchors. So it would be difficult to find the anchors just using the mesh. So or maybe it wouldn't be that difficult. Yeah, we can do that. Okay, so let's use the mesh edges component. We'll learn a bit about meshes. So you have the naked edges, and the naked edge of a mesh is an edge that is the boundary. So if you have any hole in a mesh, or in simpler words, if there is a mesh that is not surrounded by faces, then it is naked. So if it just has a face on one side, then this will be a naked edge. So to find the corners of such a mesh, we can use the naked edges. We can join them together and find the corners using discontinuity component. Why discontinuity and not the other? And why not, for instance, explode? Because if I used explode, then I would get the vertices of all the segments that create the edge. Discontinuity will only give you vertices of a curve that are discontinuities of the curve, which means that there is an angle between the previous edge and the next edge. So here we found the corners, and we will use them as anchors. Okay, let's set up Kangaroo. So we will we'll prepare to gather all the goals with a merge components, and bouncy solver again. So goals, button for resetting, Boolean toggle for turning this on and off, and yeah, that's all we need. All right, so we have the anchors. Now let's apply force to the model. So what we need to do? We need to take all the vertices of a mesh. We will deconstruct the mesh, and take them all. You could also use one of the components that are in Kangaroo, which is called mesh vertices. No, actually it's called naked vertices for some reason, because it gives you access to the naked and closed points. Naked vertices are the vertices that belong to naked edges, and closed, you understand, all the others, surrounded by faces. So you can use one of these two, whatever you prefer. All you need to get, or all you care about, is to get the vertices of the mesh. And now we will apply a force to them. So load, this is the points, and the force vector. This time it will be directed upwards. Okay, I won't input anything here. So we will put the force upwards. We will inflate, let's say, quotation mark, the model. And yeah, it just goes up because nothing holds it together. So there is no force that would keep our tent together. I'll wait a while for you. So the last thing that we need to do is we need to glue everything together. We need to apply the forces that will hold this structure together. And fortunately, we don't need to extract the edges separately, and we don't need to create the length line goals. We could, of course, just do something like that. So take the edges, both naked and interior, and create springs out of them and just input them to the model. But fortunately, there is a better component. There is a better way to do that with a mesh. It's in goal meshes, and it is called edge lengths. So it allows you to input the whole mesh together, and you just input a length factor, which will determine if your structure is more slack or more tense. And well, that's all. So you just get the edge lengths. It's a simplification of the process, let's say. So it takes all the edges and creates springs from those edges, and just input that as another goal, and this should already work for you.
There is a big difference actually in the outcome if we use mesh edges and this.
So first of all, what you get from this is just a you see a net, right? You see a mesh, but in fact this is not a mesh. What you see is a bunch of lines and nodes. It's exactly the same as before. So you have this list of null objects, and then the lines, and these lines represent the edges, but you don't get the mesh. And so you get the vertices, and you get the null objects. You could of course try to recreate the mesh from this list of vertices, because these are the only vertices in your model. If you had multiple meshes, then it would be a bit more difficult. But there is a simpler way to just pass on the geometry, pass on the mesh. And that's the answer to question that Marta had before. This is where we will use the show component. The show component allows you to pick the geometry that you want to preserve in the solver and explicitly output. So use that component and input a mesh into the show component. So I have the mesh and I input it into show, and then the show is just another goal in the on the list. And I thought that this list, or probably it is, yes. So the order matters here. So you should flatten everything at the beginning, because look what happens. If I don't flatten the inputs in merge, then I will get three lists on a data tree, which is strange, but this is how Grasshopper works. It just adds zeros to just basic lists, and then it creates a data tree. And this is why most of the times you will see that the inputs of merge are flattened or simplified in some other way. Maybe simplify would be better, or actually it would be best to just not simplify or flatten, but to use Surify before the merge. Okay, that might be a good occasion to explain to you something more about data trees. You probably already know what the data tree is, and you know such cases as this one, that you have three branches and they differ just by zeros. And the problem is that lists in Grasshopper can also have indices. So lists in Grasshopper also have paths, and simplifying won't work on lists. So simplify doesn't help here. And there is a component that will help you with that, and it is it's in basic Grasshopper. It's called Surify. And Surify just removes all those unnecessary zeros. And this is a very useful component if you work with lists. So you should use, actually, that would be the safest if you just use Surify, unless you explicitly want multiple zeros, some trailing zeros in your paths. Then Surify will help you with improper merging. So if you see this component, then just remember that it is to remove the unnecessary zeros from the paths, so that if you merge, you will get a nice flat list without any unexpected branches. And the order of goals, now I'm pretty sure of that order of goals that you input to the solver here will be also represented here. So if you input the goal show the last, then the last item of this list will be your mesh. So if you want to just get the mesh, you need to select the last item from a list. Okay, and the last thing, I suppose that would be the last interesting thing about that. Of course, you can do whatever you want later with this geometry. I will increase the strength a bit so that it is more it's shorter. And yeah, the last one, it's not very useful, but okay, sometimes it is. If you want to push your simulation a little, let's say. So there is a grab goal. Let's input that as the final on the list. And of course reset the geometry. Why is it not showing anything? Oh yeah, because it's not the last element, what Marta said. So now goal should be the first. Okay, so that's exactly what you said. So I input another goal, and then the mesh stopped being the last one. So goal is a component that allows you to, if you input it, then you can drag your model just by dragging it in Rhino viewport. So it allows you to interact for the first time with anything that was generated by your script. You can interact it with your cursor. And I said that it is not useful, but it is somehow useful if your simulation is stuck at some point and you want to push it, or if you want to test that it is actually getting back to equilibrium. So yeah, you have this jelly and you can. And I think that would be all.